Hello and a very warm welcome. In this video I will demonstrate how to perform a simulation of a complete room air conditioning system using the HVAC FEM simulator module. So I am now launching the temperature and humidity module. A complete air conditioning system is undoubtedly one of the most challenging systems to design, because it requires the designer to carry out all the essential processes for air treatment in order to maintain the specified parameters within the room. I am referring to the processes of heating, cooling, dehumidifying and humidifying. This very often causes a lot of problems. However, here on this screen we now see an example of a specific room that we implemented. Exhibit hall. Fixed conditions in a certain museum. Where our task was to maintain throughout the entire year specific required parameters, 21 degrees inside the room, and humidity not higher than, or rather not higher and not lower than 45%, which is necessary to ensure a specific microclimate for the collection stored there. Now regarding the matter of data entry, these details were already discussed in a more extensive separate video, so I won't be going over them in detail again. I would just like to briefly state that for our current subject matter, we are choosing to perform calculations utilizing both profile and climate data, as these computations will be carried out for the entirety of the year. Here we select the city and country along with the specific dates for the simulation to be carried out. Here we have the calculation mode for the automatic selection of supply air temperature and relative humidity, in order to maintain the parameters that we have set, and these parameters are then entered here into these specific input fields. And our desired temperature, as I previously mentioned, is 21 degrees Celsius and 45% humidity. Here we then set the boundary parameters within which the system is able to operate. And in this context, we are restricting the temperature of the air supply that can be effectively applied by the system. It's plus 10 degrees, and the maximum system temperature in winter can be plus 35 degrees. Here we need to input the cooler wall surface temperature. As for the internal heat gains, we will be calculating those here. I'm referring to gains from individuals occupying the room or from any other equipment. It is generally from 7 AM to 4 PM when the building normally operates. This was 23 kilowatts of sensible heat gains and 5.4 kilograms per hour of moisture gains. Since we are operating a complete air conditioning system, we have implemented a constant airflow of exactly 13,000 cubic meters per hour. And then it becomes a matter of defining later on the temperatures themselves, or using temperature data for calculations. These particular values are generally taken directly from the available climatic data. So this is precisely why these specific input fields are currently displayed as grayed out here. However, for the northern partition and also for the western partition, we have manually entered the necessary data directly from the keyboard on the opposite side of the partition, because these particular partitions are specifically marked here as internal. Now, concerning the matter of entering this data about the partitions, as I've already mentioned, these were previously discussed in a different video. I'll just add that perhaps here on the diagram that I have prepared, I will show you what I mean. If we have an asymmetrical shape of a room, or an outline of a room or building, which isn't immediately obvious here, because we only need to input the northern, southern, eastern and western partitions, we can of course have a more complex outline, tak? So we need to apply a certain type of simplification here, which is that if we see something like this, then as a rule, it's equivalent to the situation. I'll just copy the whole thing and show you what I mean. We apply a certain type of simplification because, as you can quite easily observe, this particular section of the wall is on the north side, and so is this one. So in actual fact, it all comes down to performing the appropriate classification of these partitions. And what becomes evident following this kind of transformation is that quite remarkably, no matter how the actual room has been constructed, we invariably end up with a perfectly rectangular cuboid, and therefore within these specific areas of ours. Here, I'm showing you, we simply provide the sum of all partitions on the eastern, western, northern, and southern sides, as well as the sum of the window areas. So, in fact, if we have several windows, we input the sum of those window areas into the program. We don't define them one by one. This is a simplified model for data input. We are working on making it perhaps a little more advanced. However, for engineering calculations, this type of model is entirely sufficient. Nevertheless, as I mentioned, we will be modifying it. Alright, here we also need to select the heat recovery option because we will be recovering heat and recirculating a portion of the air. The situation here is that the number of people present in this room is less than the air volume required, which is determined by the thermal humidity balance. That's just that therefore this air recirculation is absolutely indicated and required. There are no emissions of harmful pathogenic substances or things like that would prevent recirculation, so we use it. And what else? In this first simulation mode, I might intentionally force the microclimate conditions not to be maintained, just to clearly demonstrate what the proper interpretation of the results truly involves. So, Takom, I assume that first we'll be blowing air into the room, or perhaps the system can select a minimum supply air temperature of 14 degrees and the cooler coil's temperature will be 9.5 degrees. I will also explain in a moment on the psychrometric chart what this involves and how this temperature influences later processes. The matter of air dehumidification. Alright, and now having entered all this data regarding the partitions, I am running the simulation. We'll wait a moment for it to complete, and then we'll start discussing or interpreting the results. It's already apparent here in these charts that certain developments are forming. Deviations from the established target line of 45%, and this will signify that during these particular periods, this relative humidity will not be able to be maintained. Here, we also see that we are continuously generating the heat balance for this room, the balance of heating and cooling power, and the sensible heat gains, as well as the water balance, which is the amount of water that must be supplied to the system or to the room to humidify and maintain the set relative humidity, as well as dehumidified, meaning removed from the air from the room to maintain the appropriate relative humidity there. But that's for later. Once this is quick, I'll discuss it. Just
Just a moment, please. This really does take a significant amount of time, because what we are effectively doing here is performing these very specific balance sheet calculations, which must include psychometric considerations for a total of 8,640 hours across the entire year. A little longer, and calculations will be done. Okay, we have the results on all the complete charts, and what we can see here, I'll explain. This is a temperature chart. The blue dotted line shows the outdoor temperature. We can turn it off now so it doesn't obscure our view. The blue continuous line here represents the temperature graph inside the room. And here we can clearly see that this temperature was not maintained for every single period. So the plus 14 degrees we set for the air supply was not enough to maintain the interior temperature of the room at 20 to 21 degrees throughout every season of the year. These are not significant deviations, as you can clearly see, because they are in fact very minor discrepancies. We have here 21.3 degrees. However, officially for these parameters, Mochi 13,000 cubic meters per hour and a 14 degree Celsius supply, the cooling capacity was insufficient to maintain the air parameters we had requested. So in fact, regarding temperature, we are at the limit. However, what we can clearly observe is that we still have two values for Ts, which is the temperature of the supply air that the system had to achieve. To supply air and maintain a set temperature within the room, and the TSD temperature, which is the supply air temperature for the drying process. The dehumidification process involves deep cooling, then correcting this relative humidity by heating it to the supply air temperature needed to remove the remaining heat gains. In other words, we first deep cool, then heat, and only then supply air to the room. And here we can see, as we zoom in on this situation, that we are indeed seeing a certain type of such significant gaps were present. This meant that to properly dry the air, a specific condition had to be met. The system needed to drop its cooling all the way down to 14 degrees, just to condense the appropriate amount of water from the air to maintain that relative humidity in the room. And then it had to heat that air to a higher supply temperature, that's 14 to 22 degrees, to achieve the set temperature. If it blew indirectly at 14 degrees, it would simply overcool this room, and the 21 degree temperature wouldn't be maintained. It would just be colder. So the system must first cool to 14, condense the water, and to correct the relative humidity, reheat to the target supply air temperature plus 14 point. The temperature is currently 24 degrees Celsius. There are naturally some more contrasting cases of this specific type here, where, for example, the system had to go down to 14 degrees in order to properly condense the water, and then subsequently heat it up to 16. Point 1, let's say 16.1 degrees Celsius is what's needed to achieve this. What else is evident from this chart? It's also clear when, in actual fact, our entire cooling system must be fully prepared to carry out this kind of dehumidification process. And as you can clearly see here on this chart, with the ventilation parameters that we have established, the system must be ready for dehumidification, in fact, throughout the entire year. Because here we already have January, February, and so on. These are the initial periods of our year. However, the vast majority of this drying process occurs during the summer period, which is of course quite evident considering our specific climatic conditions. Nevertheless, other jakieś non-obvious issues arise from this, that in order to implement a full air conditioning process, our cooling source should be ready to perform such a process even in winter. I think that might surprise quite a few people. Next, we have the relative humidity chart. So here we can already see how this set relative humidity of 45% was shaping up and what the deviations are. We can zoom in on these to see, and we see that de facto using these boundary conditions that we imposed on the system, we will achieve a humidity of around 55%. So unfortunately, during the summer period, we certainly won't be able to maintain the set relative humidity of 45%. Instead, we will have it as high as 55%.
Yeah, okay.
And here, just as on the preceding charts, we have the option to toggle various parameters on or off. Here we can observe how the relative humidity of the supply air, the relative humidity of the air within the room, and the relative humidity of the external air are shaped. Here we have a similar scenario, though perhaps not entirely identical. Here we are examining the dependencies related to the absolute moisture content. If we disable the graph showing the absolute moisture content for the outdoor air, we can then observe how the absolute moisture content within the room behaves. This red one, so intense, with such an intense color. And what does the air look like in such a situation? The air our air conditioning system prepares. So at any given moment, what absolute moisture content must it drop to maintain the relative humidity we specified in our parameters? And here are two more interesting charts. In fact, all of them are interesting, but these I think are the most important.
This is a detailed diagram showing the heat balance of the room. And here, on this particular diagram, it appears somewhat obscured, because it incorporates within its overall scope a great number of different parameters. The most significant aspect, I believe, from the user's point of view, is the graph.
This is where the true power can be found. Of the cooling, the total cooling capacity that the system must achieve or achieves at, considering the air parameters that we wish to achieve and the maximum heating power, as well as the balance of heat gains within the room. Here, we also observe an interesting situation, particularly in winter. Even though we aim to maintain 21 degrees, the maximum heating power here, at its peak, I would say, is around 27.5 kilowatts. But interestingly, for the drying process, we need as much as 30.5 kilowatts of heat. So this heat source must also be operational year-round and ensure we can achieve the desired parameters. However, I'll come back to that shortly. What was I going to say? We also have here a different kind of chart. Maybe I'll turn this off for illustration. This is exactly what the graph of sensible heat gains in the room looks like. So, as you can see here, we have heat losses during the winter period through the building's partitions, and these amount to, we could say, minus 14 to minus 15 kilowatts. While the total gains from all sources, from equipment, lighting, solar radiation, and so on, amount to 31 kilowatts. However, here we have a graph of the water balance. And here, I'll also go ahead and disable a few specific things. I'll just keep the water mass here. That's used for both humidification and dehumidification. Then we also have the water mass designated for accumulation, and the water mass that is, let's say, either supplied to or removed from the system by the infiltration air. And here we have our moisture gains, which we defined in these temporal variables. These are the gains, so they are also shown here on this chart as this blue line, but I'm turning it off now just to make it a little bit so it wouldn't obscure it. And now here we can see that everything that is above the zero line is water, which must be the air, it must be humidified in this particular situation. And here, as you can clearly see, there are also situations where we need to dry out this very air in certain places. However, everything below zero means water must be removed from the room to dry the room and the supply air, which physically dries the room. Okay. However, what we deduce from this analysis is that we essentially weren't able to maintain our preset air parameters that we had aimed for, because we did not reach 45% humidity and 21 degrees Celsius. We only achieved one could say that perhaps even the 21 degrees were achieved with minor deviations, but the relative humidity has most certainly been exceeded. This means that we will have to implement deeper cooling in order to condense more water on the chiller unit. And we achieve this by assuming that I can use a minimum supply air temperature of 10 degrees Celsius. And I also assume the cooler wall temperature to be 5 degrees Celsius. I'm entering the data here because I know that under these specific circumstances, this simulation will now run in the proper way, because that was the main objective of this project. And then we show, or rather we simulate, and then we present the results. How will this look now? We can already see a straight line across the board for the room's parameters. In other words, we have no deviations from the set temperature of 21 degrees and humidity of 45%. We are successfully able to achieve this. This means that the parameters have been properly selected. Please observe that in no way, at no point have we even touched the psychrometric chart yet, and we are already obtaining full results, and that's including accumulation. The accumulation of heat in partitions, the accumulation of moisture in partitions, and the accumulation of heat and moisture in the equipment of this room, which is also defined in this very place.
Just one more moment.
Yes, and here we can clearly see that we've successfully achieved the planned parameters throughout the entire year. There are no longer any deviations from that. Here we also see the situation regarding dehumidifying the air, and that's the situation we're in. This is a temperature chart which is required solely for achieving a specific temperature, and here we have it considering the temperature that must be reached for drying. And here we can see that the system never dropped, not even to plus 10 degrees Celsius. The temperature dropped slightly for us down to about 11 degrees, and then the heating process began. I'll zoom in on this now so I can show it to you perhaps in a more visually interesting spot. And this was the situation that at approximately the 5125th hour, it happened that for a certain combination of intake air parameters, temperature and relative humidity, of course, taking into account heat recovery, recirculation, and so on, the system had to process such air by cooling it to plus 11 degrees, then heating it, and correcting the relative humidity in order to relative humidity adjustments to be heated to a temperature of 13.5 degrees and only then blown into the room to achieve a final temperature of 21 degrees. Here we have a graph of relative humidity. And also, if we examine it closely, you won't see any erratic movements or fluctuations on the chart. So, in other words, the system is fully capable of achieving these specific parameters of both temperature and humidity under any chosen climate conditions. The exact same principle will obviously apply here in the context of the absolute moisture content. There is no other way. And here the balance of heat and moisture. Here we'll see an increase in heating and cooling power. There we had 40-something kilowatts of cooling power, but that was because we didn't achieve our relative humidity, as the system only went down to a minimum of 14 degrees. Now it can drop to plus 10 degrees, so it will automatically, wanting to achieve this relative humidity, cool more deeply, and consequently will need more cooling power, which in this situation will be equal to about 63 kilowatts as a peak demand. However, the heating power at its peak will be 37.6 kilowatts. So that's how the situation looks regarding the interpretation of these results. And then there's also the matter of the moisture balance. Here we also see that in winter we need to, at most, in November, December, we have 15.2 kilograms for humidifying the air. And for drying, for condensation, we will have to condense this much water, maybe here still approximately 24 kilograms of moisture per hour. With such an analysis completed, we can of course export it here as a report. We click OK and wait a few moments.
Just a moment until this report is created for us here.
This is the way it appears.
So we have all of our charts and graphs ready. Now I'd like to show you on the psychrometric chart what exactly is meant by these specific parameters of the cooler wall temperature that we are demonstrating. Specifically, it's about a situation where if we have, let's say, a point 1 representing the parameters of the intake air, let's say 30 degrees wet bulb, dry bulb temperature, and 45% humidity. And now we have the temperature of the cooler wall, plus 5 degrees, and the humidity in this situation is 100%. This is the temperature at which water condenses on the cooler surface. Now we are bringing about for ourselves a transformation. Yes, and this is our temperature or the transformation that presents the maximum temperature or the coolest parameters. However, we can go down to a minimum temperature of plus 10 degrees. So we add the cooler point as a minimum of 10 degrees. We mark it so it's highlighted on the process line. and here it comes out at this point. During the cooling process we can go down to this specific point at a minimum, and then we need to heat it up to the target temperature for our air supply, so we call it N. And here let's assume that after a thorough drying process we want to warm this up to a temperature of 14 degrees Celsius. The absolute moisture content here is 6.7. Okay, and we can also, let's say, add these processes, how they will proceed within the air conditioning unit. So here we have from point 1 to the cooling coil.
And we also have the actual transformation of the air supply.
Yes, this is precisely how it will, in reality, manifest itself to us. This is the minimum temperature of the cooling unit's wall, which is defined and directly dependent on the source of cold. However, this represents our supply air temperature, which is achieved through the adjustment of the temperature to which we can minimally cool down and then reheat secondarily on the secondary heating coil. Yes, and that's pretty much everything I wanted to show you in this video. I'll show an identical video for the other computational modes, but that's all for this video. Thank you for your attention. I hope I've shed some light on how this module can be effectively used in your projects. Thanks, and I'll see you in the next video.
Hello,